get rid of water. So let's take a look at the observed reaction. So the observed reaction takes an alcohol, and then we have reversible arrows here, and then we need to put in sulfuric acid. Now, the type of acid is important. It actually has to be concentrated. So if you remember back from GChem, those little brackets just mean concentrated, right? And that concentrated acid has a low concentration of water in it. So that's going to be important too, because this is an equilibrium reaction. And when you lose water as a product, right, it's there. So by Le Chatelier's, if you had a lot of water present, it would shift the equilibrium in the back direction. So we want to keep that concentration low. And then the other product that we get is we get the alkene. Okay? Now let's take a look at the mechanism. So it's a pretty straightforward thing. Let's zoom in a little bit so we can make it look good. Let's take that same alcohol there and let's dehydrate it. So we're going to go through and we're going to add H2SO4. So H2SO4 has the following Lewis structure. Take a second, put that in. Right now, what happens, and this is kind of an interesting thing that we're going to see happening later, is that this group right here, that group is by itself a bad leaving group. Right, recall that weak bases are good leaving groups. Hydroxide is a strong base, right? So we don't need to look at a pK table to figure something like that out. We just know that that's the case. So the first step is we're going to convert this bad leaving group into a good leaving group. And we're going to do that by taking a set of electrons here and grabbing an H atom. And so that oxygen there, that's your nucleophile. And then we're kicking that guy off. Okay. Now the intermediate that we get next is this guy. So it's got an H there. Lost a set of electrons to the other H, and now it's a carbocation. And then we get HSO4 minus here too, right? But that thing we don't usually write out. Okay. Now this, and this is kind of the important point here, this is now a good leaving group. So we can see a continuation of this reaction then, because we can just kick off our leaving group. That step happens a lot in biochemistry. We see that water's a leaving group in a lot of reactions. Form a positive charge here. And then the last step, I'm just going to write this out, CH2H. Right, so that's kind of like your alpha. All of the beta positions could do an elimination. In this case, you get one product, but if that led to a mixture of different alkenes with cis and trans, you could get a bunch there. Right, and the last step of this thing is we're going to take the oxygen. I'm going to write this out this way for you guys. Of hydrogen sulfate to grab one of those H's. So it's going to come down here, grab an H, and then that's going to give you your double bond. So what we get is our alkene here, and then I want to include, just for the sake of showing this, that sulfuric acid is being made here. So the acid helps the leaving group become a better leaving group, right? The OH becomes an OH2+, but it's regenerated. So when something like that happens in chemistry, we say that it's a catalyst, right? So a couple bullet points about this. If you look down below here, notice it's at equilibrium, right? We saw water is a product. Again, we must use that low concentration, and we said it's because sulfuric acid, it's concentrated, right? That provides us with that low concentration of H2O. It's catalyzed, so there's a catalyst here. They participate in the reaction, but they're not consumed. So that's also very important. And then the other thing, the last thing just to point out here is, you form a carbocation. So just like in E1s, when that happens, rearrangements are possible, right? So that's going to accompany this in situations in which you might have the opportunity for a hydride or a methyl shift. All right, guys, so that's the end of chapter 7. So we'll see you next time when we start talking about chapter 8.